Hi, everyone. Hope you guys are all well and keeping safe. Where I feel like we're almost done with COVID, just a little bit longer, hopefully. The title is a little bit over the top, the future of governing equations. Maybe you could just think about it as my own little personal journey right now, currently, in trying to, actually, machine learning methods and AI have really been forcing me to contemplate a little bit of what I think about governing equations. I'm very much a governing equations type of person. I come from a background where I think about PDEs and ODEs as sort of the models that we build physics from. And now I'm in a place where I've got to rethink that a little bit. And I'm going to show you this a little bit with some of the examples I give. And my hope is to sort of just, I don't know, maybe open your perspective up a little bit. Certainly, the techniques that we have that are emerging are opening up my perspective. And so hopefully this can be some helpful thoughts for you. Okay, so I always start with this here, this slide, which is, I like to frame this in terms of context in a way that I think is intuitive. So I give this as, what you're looking at here is the night sky. It was sort of, in some sense, the first physics problem we had. Right, the first and longest lasting physics problem, right, which is understanding the celestial mechanics, right? So what you're looking at here in the night sky is, this is the retrograde motion of Mars, that's the foreground. And over here on the left is the retrograde motion of Saturn, excuse me. And so you have these two planets, and a lot of the ancient world was interested in predicting the motion of these planets. And so we were trying to come up with certainly predictive models and trying to understand this. The motion of these planets were quite fascinating, and so they took on the name of the Greek or Roman gods, and if they aligned up, things could happen, and we had portents in the sky. So because this is such an important thing, because before electricity, all you had to do was look up in the sky, and you would see this every single night, right? And this is kind of unlike today, where we have light pollution, so you don't really pay that much attention to the stars, maybe. But the first theory really to produce sort of a predictive model in terms of a mathematical construct was this doctrine of the perfect circle. It came out of 2nd century Alexandria, Egypt, the Ptolemaic dynasty there. Claudius Ptolemy was a scientist there. This was sort of the intellectual heart of the world. And the idea was that you could describe this retrograde motion as circles upon circles. So this was the doctrine of the perfect circle. And this is this beautiful graphic, which is a Renaissance painting of this sort of kind of this model that they had for this. It's kind of an interesting thing. One way to think about this first model was that this was the earliest version of a Fourier transform, right? If you want to think about this way, you can think about I'm going to represent all these motions as just a bunch of orbits or periods of circles. And so you could add up a bunch of circles and you could get just like a Fourier mode expansion is one way to think about this. So this theory lasted for quite a long time until we really changed coordinate systems. And this was really from Copernicus advocating this idea, but really it was the work of Galileo and Kepler that set the foundations for this coordinate transformation. And so through their mathematical architectures, they were able to say, hey, let's move. Maybe what we should really do is have a heliocentric coordinate system, and that the retrograde motion is just simply an observational effect of these planets revolving around the sun in elliptic orbits. And by the way, this coordinate transformation becomes very important because once you have the right coordinate system, you can write down this governing equation, which is F equals ma, which is what Newton did about 100 years later. So you really needed to have the good coordinate system in place in order for you to get to that next step, which is write down a governing equation. In the late 1800s, as we got better and better, however, observational data, there were some discrepancies between this F equals ma physics and what was actually observed in the orbits of these planets, especially for some of the bigger planets. At first they thought, well, maybe there's another planet we just didn't pick up somewhere. But it turns out it was through these improved measurements that we were able to, actually what Einstein was able to do is propose this general relativity theory, which stated that gravity actually was warping space-time local to high gravitational fields. And the only way you can get that is through these improved measurement capabilities. So every time we take better measurements, we're going to get better theories, better models. And I think it's true today as it was true here. And this is kind of exciting. So the whole data revolution, we always talk about data science, machine learning. This whole revolution is about sensors. It's all about sensors. It's the fact that we can produce sensors, monitor everything cheaply, pull in very high precision data in so many different applications that we could never do before. And that's what's really driving all of this AI architecture is it's a sensor technology issue. And I think that's kind of exciting for us to be thinking about. All right. So now what do we do with this? Let's talk about models. And I'm going to start framing this so we can start setting up the architecture of how can we use our machine learning methods to help us build these models for us. Now, the first model I want to talk about here is the Ptolemaic model. So think about it this way. I want to take data. The data is the observation of the night sky. It is pixel space. It's a picture of the night sky, and it's different snapshots of the night sky. And that is my input. And what I want here, I'm already framing this in terms of neural networks. What I would like to do is I'd like my neural network to learn a coordinate transformation in which I can express my model and then come back out. So this is like an autoencoder structure, which takes pixel space, which is artificially very high dimensional, and brings me down into a low dimensional representation of the dynamics. And for what Ptolemy did, what you'd really like to do is say, I'd like this transformation to produce this circles on circles theory for me here in this middle layer. In other words, really produce a Fourier decomposition for me for the planets, right? So that's one model that we could do. A second model is more of the Newtonian model, which is take the data in. What I need to learn is a transformation now, not to the Ptolemaic model, but instead to the heliocentric coordinate system, in which in this middle layer now, I can write down F equals ma, do predictions and forecasting, and I can also come back out to the original coordinate system. So, by the way, this is interesting because to some extent, we always think of this second model as the right model, right? I learn the heliocentric coordinate system, I get F equals ma, but really this model can produce just as accurate results if you're going to do a forecast, for instance. So the question is, you know, I don't know if I want to make a judgment statement here. I just want to say that these models, there are different ways to approach it, even though we kind of think of one as being correct, in other words, to be able to get our governing equation out, there are a lot of options for us here. And it really starts to highlight that Kepler and Newton had different ways to think about this. So Kepler really, right, so constructing these orbits, he said, look, I can do a regression. He had Tycho Brahe's data. It took him 11 years from that data to produce his Tableau Nouveau, which had sort of these elliptic orbits in it. And the reason it took 11 years is because he didn't have MATLAB or Python. Otherwise, it would have taken him like a couple weeks, right? Just use some code, do a regression, find your elliptic orbits. But instead, he had to do all this by hand with lots of different models, all by hand. But what he did is an interpolation, right? He took these orbits, he fit a model to it. The big deal with Newton, right, that we recognize with the governing equation is that once you have a governing equation, not only can you produce the solutions that Kepler had, but then you can imagine sort of launching somebody to space, right? You could say, I want to put a rocket, put it in orbit around the moon and come back. And it's never, I don't have a data set that's ever seen this. So if I'm going to send Neil Armstrong up there to land on the moon and come back, I better have good governing equations to make that prediction and to make the right scientific call for that. So that's the power of that kind of idea, is that a governing equation buys you quite a bit. However, I want to come back then to this idea of governing equations. And I want to give you the paradigm of when we think about learning and the models and what we can learn, there are a lot of different things we can decide to actually learn. So here's the paradigm I want to give you. I want to give you the Burger's equation. So for me, growing up in applied math, this is sort of a standard equation where you'd get some It's some kind of wave propagation, which speed is dependent upon the amplitude. This creates shock structures. And so often to regularize the shock, you put a little bit of diffusive regularization. So it's just a standard model that people use quite a bit in applied math. And let's call this the truth. So this is one way to represent sort of some kind of system, is say, here are the governing equations for the system. And in some sense, we say that's a really important step. But here's the thing. This is the thought process now that I am going through with this, which is, even if I write this PDE down as the truth model, what do I do with it? Well, we have a whole curriculum here in applied math that teaches people how to solve this. So in other words, I could stay with this, or it was recognized in 1949, 1950, independently by Cole and Hopf, that there's this transformation of this equation, known as the Cole-Hopf transformation, that turns this nonlinear PDE to a linear heat equation. You say, well, I just traded PDEs in a different coordinate system. I have a different representation. By the way, the great thing about this new representation, it's linear, and it's 2 terms instead of 3. So somehow I've moved myself potentially into a much better coordinate system. But even if I had this PDE, I'd still have to solve it. So you could imagine doing some kind of eigenfunction separation of variables and solving this. Here's, let's say, maybe a representation of that solution. And of course, you'd say, great, I now have the solution. So notice these are all equivalent. And by the way, I would never actually sum to infinity, right? Because that's impossible. You'd actually sum to some large n. So what I'm showing here on this left side are representations or manifestations all of the same thing. I could represent this dynamics in the original variable, in this new variable, in the actual solution space, right? Or I could actually just produce the solution here. There it is. Like, say I've added this up and say, well, why not just store the original data? Okay, so these are all manifestations of all representations, different representations of that governing equations. Okay, another route is to just discretize and solve, right? So this is like, for instance, representing some kind of discretization scheme of this governing equation. And so I could say, well, that's maybe a good representation, because now if you need to generate solutions, I just put it into this iterative scheme and march it forward in time and producing the solution. So I want to focus on these 4 representations of this PDE. So this is the PDE. But if I give you this PDE, I say, you know what, I'd really like to know, what is u at time 1000 and x equals 7? This PDE can't tell you that. You actually have to either solve it through numerics or use your solution expression here to get that and to be able to construct this. Or if you just had the data, you could just have a lookup table. So the question really comes for us now then, when we start to think about these machine learning paradigms, is what should I actually learn? I have choices. I could learn any of these representations of that PDE. And so in some sense, this model right here is where I actually have the expansion. This is very much like the Ptolemaic model that I showed you, right? This is the circles on circles. This is an expression that you add some frequencies to get a solution. And up here, this is your F equals MA. So, and then this is the more modern version, which is the computational scheme. Or I could just save the data directly. So I have options now when I go to a physics system. I don't just necessarily go learn a governing equation, because if I learn the governing equation, the first thing you're going to do is going to go have to solve it. Why not just learn the solutions directly then? Okay, so these are the kind of thoughts that you can start to think about when you do a modeling. And by the way, I want to give an analogy here, because I think this is what struck my mind a little bit about this. A governing equation, it's a little bit like DNA, right? So here's DNA. From this DNA, you can produce people, right? But if you say, what does a person look like? Well, if it's a DNA strand, you have to actually grow a person for 18 years until it produces a person. And subject to their environment, which might be boundary conditions, initial conditions, all these people come out differently. So in some sense, people are like the simulation of the DNA. So these people are like the actual data itself. It's expensive to generate it, and you get quite a bit of diversity. So these are realizations of each different pieces of DNA. So even though the DNA is this very compact version or representation, just like the governing equation itself can't tell me anything of what a person looks like until I actually run that whole thing to produce a solution. So somehow we feel like we need to balance out what we want to learn here, right? Because if I really need that to give you values of data, I have to actually do the simulation. But if I just want to give you some kind of high level representation, the DNA is the right, or the governing equation is the right version. So again, it tells us a little bit about what should we be learning. So let's get into the details a little bit then, and talk about a mathematical framework. So here's the generic mathematical framework I think about, which is I have measurements, and then I have some dynamics. And I don't necessarily know the dynamical system, the governing equations, nor do I know how my measurements map to the state space variable. And so this is a very ill-posed problem. And so the question is, how do you regularize it? And the way we're going to regularize it is to start imposing constraints. And so I'm going to talk about the constraints that are available to us to impose on this. The first thing to do is why don't we just, try to learn a coordinate system where the dynamics is linear. So this is a little bit like the Burger's equation. Why not just take data and learn directly what the Kohl-Hopf transform gave us, which is a linear heat equation. So we're going to try to learn linear models. And the reason we like linear models is because essentially they have exponential solutions. So we can just basically say, if I get a linear model, I can put an e to lambda t or e to lambda x as a solution, and I'm going to get solutions out very nicely for us. And lambda, of course, can be complex, so I can get sines and cosines and so forth. So this is what we have started with, and this is very closely related to the ideas of Koopman theory. Koopman theory is about figuring out how to embed nonlinear dynamics into the right coordinate system, right set of observables, which makes the dynamics linear. So here is the idea behind this. So I'm going to go ahead. This is work with Bethany Lush, who's now at Argonne National Labs. But Bethany trained a neural network, and so she said, let's go ahead and take our original input space, and this is actually going to be for us try to encode a pendulum, fully nonlinear pendulums. Theta double dot equals minus sine theta. So it's a nonlinear dynamical system, and what I'd like to do is take my input variables, which is the measurements of that system, learn a coordinate transformation to a new variable. And what I want to have happen in this latent space is that when I go from y of k to y of k plus 1, in other words, when I take a time step forward, is that there's a linear map that does this. Okay, so I'm trying to build a Koopman operator for the pendulum. In fact, you can actually train a neural network to do this as long as you parameterize this linear operator, which is two-dimensional. And by the way, I want to keep this middle layer two-dimensional because we know that the physics of that system is two-dimensional. A pendulum can be completely characterized by theta theta dot. So why would you go to a high dimensional space here? It's very easy in neural networks just to go to very high dimensional space, work in the high dimensional space. But if I know my physics is two-dimensional, you're kind of, well, okay, I don't want to say you're doing it wrong, but from my own perspective, I think part of what we want to do in physics discovery and engineering process discovery is to really keep this at the dimensionality of the actual physics. So we're going to constrain this to two dimensions. And in order to do that, we have to parameterize this linear operator by the frequency of the oscillations. And so we can actually take this fully nonlinear pendulum. Here it is. Here's the phase plane of the pendulum. Here's these, as you start seeing the oscillations get bigger, it becomes more, these oscillations move away from being purely sinusoidal. And what we can do with this is learn a transformation to make it completely linear, all the way up to the saddle, which is at the top. And here are the transformations that neural network, these nonlinear eigenfunctions that take me to this new coordinate system. So this allows you then to make this nonlinear pendulum linear all the way up to that saddle. Okay, so you've handled the nonlinearity, you've encoded it into this new coordinate system, very much like that Kohlhoff transform. We took this idea and said, okay, can we do harder problems? The pendulum is pretty easy. And this is work with Craig Jin. And what Craig did is said, yeah, actually, let's go ahead and try this. And what we did is we did this with the Kuromoto-Shibashinsky PDE. So this is a model for spatial temporal dynamics, which produces spatial temporal chaos. It's very difficult PDE to think that we could actually encode it in linear space. But in fact, Craig was able to do this. So it's very much like the inverse scattering transform, which allows us to linearize certain completely integral PDEs. But what Craig was able to do is take this dissipative chaotic PDE and embed it in a linear operator. And so you take your initial measurement space, you learn a latent representation where there's a linear operator there. And all you're seeing here on the right is the full simulations of the solution. And this is what this linear network gives you. Again, coming into the autoencoder, out of the autoencoder, and you basically get this thing perfectly. So it's telling you that you can embed something like as complex as the Kuromoto-Shibashinsky equation in a linear operator. So this is very much like the Kohlhoff transform idea. And you could also say, why don't I just learn this? Because now that I have a linear operator, I can look at its eigenfunctions, eigenvalues, and tell you everything I want to about this system because I have a really great coordinate system to do that. So what I've been doing here is warping space to make things linear. I could also warp time to make things linear. This goes right to the Ptolemaic idea, which is, this is work with Henning Lange. He's a postdoc here. And what Henning did is said, look, I have some time series, and there's a very nice way to represent time series, which is through Fourier modes, which, you know, we've been doing forever. A lot of times, though, when you do a fast Fourier transform or a Fourier decomposition, you're constrained to periodic boundary conditions. So there's two things here that happened that Henning did. One is he removed the constraint of having periodic boundary conditions. He said, look, just fit the data to the best sines and cosines available to you. Here they are, without the constraint of periodicity at the boundaries. And so this turns out to be able to do that. It sets it up as an optimization problem where you have to use gradient descent to find the fewest number of Fourier modes, not constrained anymore by periodic boundary conditions, to fit the data. The second thing is that Henning did, he said, look, signals like I'm showing you here, where they're sharp, require a lot of Fourier modes. And so instead of using a lot of Fourier modes, why not, in fact, transform this time series to something that looks more and more sinusoidal? So what he did is said, you can take some of these complex time series and through a neural network, transform the data to make it look as sinusoidal as possible, then fit it to sinusoids. So in the right coordinate system, this thing looks really like a small number of Fourier modes can represent it. So think about a sawtooth wave. A sawtooth wave is clearly like a very simple periodic object. But in Fourier representation, it costs you a ton of Fourier modes. What Henning does here is just learns a new neural network transformation to take that sawtooth, transforms it into a sine, and then it's a single Fourier mode. So in doing things like this, you can actually do an amazing job to start to think about forecasting. And by the way, you can do this in time, but you can also do this in space, right? So if you're doing boundary value problems, which might be more relevant for materials, you can use all this architecture there as well. So here's how this Koopman forecasting algorithm works. You can see that the errors are significantly lower than if you use sort of these state-of-the-art LSTM, GRU echo state networks, there was all the modern recurrent neural network architectures that people would always say use that on time series. This method does significantly better, as well as more standard statistical methods like ARIMA. Okay, so when you use the right tools and the right methods, and again, this is basically what Ptolemy did. Expand in sines and cosines. But here we warp the data first so that representation is really quite ideal. You can make nice reduced order models with this. So this is a full PD simulation of cavity flow. And you can see here the flow dynamics. And if you look at the low dimensional subspace, so take snapshots of this, do an SVD, and look at the dominant modes, you can take the time series data and use this method of Henning to reshape that into Fourier modes. And what you do here is this is your now prediction of this model. It does an amazing job. And not only that, you're no longer this is trivial to compute. Now you say, I want the solution at time 1,000,000. You just plug in t equals 1,000,000, put your solution there. I don't have to forward simulate this all the way to 1,000,000, which is extremely costly. This just gets it for me very easy. In other words, I have the solution parameterized at all time. Okay. So this is one way to go, is to say, let's learn a linear model. I could also stay back with this idea of governing equations to begin with. What if I just wanted to take data and try to come to this concept of, well, we talked about learning dynamics. Well, here you go. You can do this, what's called sparse identification nonlinear dynamics, SIND, which is you could take data and learn governing equations from it. So if you take data and learn governing equations from it, the idea is I give you time series data, and it's some model like x dot equals f of x. You don't know what f of x is. So, but you can take the data I give you, x, differentiate it. That's over here. F of x, not sure what it is, but you build a library of potential terms. So every column here is a library of a potential term that might be part of the dynamics. And I have a whole library of books here that I could inspire what that library might look like, because we've all studied physics and engineering. We have lots of governing equations knowledge. So we just do a regression onto that library. And what we believe, if you believe in dominant balanced physics, there should be only a few library terms that matter for describing the physics. And so you do this. This is basically an AX equal to B, a linear solve where you're promoting a sparse solution. In other words, I want as few library terms on as possible to represent this dynamics. Okay. All right. You can do this for PDEs, and here they are. So this is work with Sam Rudy, where he took all of these PDEs. You just give me spatial temporal data, and this learns the PDE that generated that data. And by the way, for those of you interested, we just upgraded what's called the PySyndy package with a bunch of new features and much more robust to noise. We have ensembling, a weak formulation of these PDEs and ODEs. So if you're interested in using SIND, we have a really good architecture out there now in what was just released, PySyndy 2. Okay. All right, so for the PDE then, I didn't tell you that we had to discover coordinates and dynamics. We just said I knew the right state space. But here I want to think about learning coordinates and dynamics together. This is actually where I think we can make a lot of progress. So this is work with Kathleen, and I think Kathleen's work really picks up all the things we do from the physics perspective, which is very much like the planetary motion, which is I have to learn the coordinate system, heliocentric universe, then I can learn F equals ma. So what Kathleen has here is that kind of architecture. I want to learn a coordinate system in which to represent my governing equations, and then I'm going to impose SIND in that area. So this combination allows you some really interesting results, including the fact that here's what I'm going to do. This is what Kathleen was able to do. Take something like a pendulum. But now the pendulum is, I'm just going to give you the video of the pendulum. So there's the video. The algorithm has no concept that there's a pendulum in there, that there's a theta theta dot. But what this thing does is it learns a coordinate transformation, and it learns what theta theta and dot are. In other words, the whole neural net, the entire objective is to learn this coordinate system so that in this coordinate system, it can write down this model. This is what it discovers. So you see the discovery pipeline is very natural. We take data from this high dimensional state space, and what this thing learns is a latent representation where there's a parsimonious physics model underneath there describing the dynamics itself. All right, so everything I've assumed so far assumes that we have no physics knowledge. So let's actually bring some physics knowledge in, right? Presumably everybody's on this call because you actually have studied physics for a while at some point in your life, right? And so you have books and you learn some physics, and it's kind of a dumb idea just to throw out what you learned and let the computer work on its own as if it had no information. So how do you start to inform your model building procedure that you actually know some physics? So this is work with Karti Kahaman and Megan Evers. In fact, Megan's paper will be up on the archive probably within the next week or two. And I like this paper a lot that Megan did, because what it's really starting to highlight is, look, it's pretty rare we come to a problem where we don't know anything. We actually know quite a bit about the problems we study, right? We've had F equals ma type physics models, first principles modeling capabilities. So why don't we start off with the fact that we actually have some information about that physics system? The problem is when we actually take measurements, sometimes we're like, well, I know some things to be true, but when I look at the data in my model, they don't match up very well. So I'm missing some physics. So the question is how to use this just to learn the missing physics. And this Cindy architecture, it's very natural to do this in. Remember that this thing was set up as just an x equal to b, where if I had the derivative of the system, then I just regressed to a library of potential terms. Now, if I know f of x, in other words, I know some terms, I just move it over to the left-hand side. And now this part of in the x equal to b is part of the b. And then I just build the library for the potential discrepancy term. So it's a very natural framework, very easy to adjust in this. And then now you're making use of physics knowledge that you have. Okay. And where this becomes important is for things like this digital twin. So imagine the following. Here is an actual robot arm, and on the left is your CAD-based sim. And presumably they're like, the CAD-based sim is like this platonic model for this robot arm. In other words, it's a perfect model. There's no frictional forces and things like this. The problem is on a manufacturing floor, this CAD-based model is not accurate enough to actually model an assembly line. However, if you had sensors and you collected data off of this real robot arm, you could imagine basically using this discrepancy modeling framework to build a model for all of the missing physics that you have here in order for you to make this CAD-based model actually match reality. And so this is an architecture where I think this discrepancy modeling framework can play a big role. Okay. All right. So let's back away even further from then physics-based models. And I'm just going to start thinking about time stepping. You can, if you're solving a PDE or a ODE, whether it's boundary value problem or time initialization problem, this kind of architecture I'm going to show you here is actually quite powerful. This is with Yu-Ying Liu. And what we're going to think about, I'm going to talk about it in terms of time stepping, but again, you can use it in terms of spatial dynamics as well, or boundary value problems. I'm just going to think about flow maps. Flow maps are a way to learn how do I get from time t to t plus delta t. Now, a lot of times this flow map, if we take delta t small, a Runge-Kutta scheme is a flow map, right? It tells you how to go from time t to t plus delta t through some kind of, this 4-step process. So time stepping algorithms are constrained by Taylor series expansions. In other words, the accuracy in those schemes are completely dictated by a Taylor series expansion around time t to get into t plus delta t. However, a neural network doesn't have such constraints. If you have rich data, you can actually just say, look, I want to learn flow maps for long time scale steps, medium time scale steps, small time scale steps. And you want to integrate it together so that you can learn how to go big, small, and medium steps very efficiently. And this is what Yu-Ying did. And so if you want to do a long time simulation, you can get around some of the numerical stiffness issues that you would have by resolving the very fast time scale physics, because this integrated structure allows you to take really big steps into the future and then refine your steps in time later on. And it's done in an architecture where it's all brought together. And so now you can have this very efficient time stepper that gets around you numerical stiffness issues. This architecture has here we go, applied on some PDE systems, as well as music score and a video. And you can see that this method works significantly better than your standard LSTM, echo state networks, clockwork, recurrent neural networks. It's just a superior object because you're really bringing in sort of this dynamical systems angle into this way of thinking about things. So anyway, I think everything that we've learned from our textbooks mathematically, you can say, hey, what if I built that kind of objects directly for myself with these neural networks? And if you start to use that knowledge, your physics-based knowledge here, you can actually make great progress with things. Final thoughts, and this is around a model compression idea. If you remember, I started at the beginning, I started talking about I could learn the governing equation, but if I wanted to give, if you asked me for what's the value of the flow field at a certain time in a certain location, the governing equations couldn't tell you that. You'd have to actually simulate them to produce that information. But if I just give you the full data, you can look it up, but it's really huge. So we want to think about model compression. How do I balance this sort of DNA versus people kind of argument, or governing equations versus actual simulation data? So this is work that Xiaolu Pan did. And what he trains is this, what we call it neural implicit flow, which is he trains a hyperparameter network, which is he trains a network that takes the spatial information into a neural network mapping space to the actual value. And there's a parameter net which parameterizes this dynamics. And this is the external factors. We treat time as an external factor as well as any other parameters like Reynolds number, for instance, in flow physics. Also, sensor locations in this. So what ends up happening is when you train this, now you have this very compact representation of your physics. So for instance, you could take multiscale spatial temporal data. This is full turbulent flow fields from the Johns Hopkins database, which is really huge. And you can basically encode this all in this mesh agnostic. It's completely mesh agnostic. It doesn't really even care that maybe you have data that has different meshes or different sampling locations. You can train it all on this. And what you end up getting is a compact representation of all that physics. So this is almost an ideal representation because you do away with having all this very high dimensional data. So if you ask me, what's the flow field at some specific location and time, the data itself is massive. And if you give me the governing equations, they're almost worthless to get you a time thing, an actual value there, unless I run the simulation. And this sort of brings you these two together into this very compact representation of the space-time dynamics. And so you can build back out. Here you go. At the bottom, this is your representation encoded in this network of the full turbulent flow physics. So it's a really clever architecture from Xiaolu's perspective. I think that this paper will also be up on the archive probably within the next couple of weeks. So, final thoughts. Ultimately, everything was around this concept of parsimony in our models, whether it's a linear model, it's very small, or whether it's a governing equation, it's very small, or even this compactification at the end is very small. We were always trying to regularize this data-driven discovery process into some kind of parsimonious representation. And like I started off with at the beginning, there are a lot of different ways you can do this, and there's a lot of ways to represent this solution. Governing equations are only one way to do it. You can just directly learn a linear model or directly learn the solution to the linear model. And so anyway, when you start thinking more broadly, it actually offers us all as scientists a lot of interesting possibilities of how we do engineering and physics design. So thanks so much for your time.